Greetings YouTubers, and welcome to the long-delayed episode 7 of my ongoing series, Lies That Flerfs Tell. Today we're considering everybody's favourite piece of flat earth sloganeering, Earth measures flat. This singularly vacuous assertion plays a particularly prominent role in the religious ceremonies conducted by Nathan Oakley and his odious colleagues. In this context, it plays a conspicuous role in Oakley's attempts to program the members of his cult through ritualistic call and response and simple-minded repetition. In particular, it serves as an easily remembered and readily regurgitated mantra that cult members can recite whenever their beliefs are challenged. It can then be reflexively deployed to short-circuit any conversation that might require Oakley's followers to substantiate their belief system, thus allowing them to neatly sidestep any requirement that they support their position with either observational evidence or logical argumentation. Oakley's support for his position, insomuch as he has any, is that somehow elevation angles require that horizontal planes correspond to some physical reality. To deconstruct exactly why this claim is simply unfounded, I'm going to have to go over some introductory concepts from geometry. Hopefully the next few moments won't be too tedious for anybody who does understand geometry, but for everybody else this might be a useful refresher. So let's start with a fairly fundamental question: what is an angle? This question, as simple as it seems, overlooks a technicality in that there are different types of angles, so we're restricting our attention here to Euclidean or plane angles, angles that are inside a planar surface. In planar geometry, an angle is the figure formed by two rays sharing a common endpoint. Most familiarly, angles are measured in units of degrees, with 360 degrees defining a full rotation. For reasons of computational convenience, mathematicians and physicists prefer to measure angles using radians, with 2 pi radians defining a full rotation. Which is all well and good, but the more keen-eyed among you will have noticed that we have introduced a new concept without defining it. What the hell is a ray? A ray is a geometric element closely related to a line. In fact, another name for a ray is a half line. So just like a line, a ray is defined by two non-identical or non-degenerate points. Throughout this discussion, I will label points using letters from the English alphabet, in this case A and B. There is then a uniquely defined line passing through A and B and extending infinitely in either direction. Note that there is no requirement in this definition that either point A or point B lie on a physical surface, nor that the line between them coincide with a physical surface or indeed intersect a physical surface at any point. Having defined the line between A and B, we now move on to derive the ray by picking one of our points as an initial point of the ray. In this case, we will let A be the initial point. Our ray is then the set of all points lying on the line, starting from A and extending in the direction of B. The ray is defined to extend infinitely in that direction, so even the points beyond B lie on the ray. I will reiterate here that there is no requirement that either point A or point B lie on a physical surface, nor that the ray defined by them coincide with or intersect a physical surface at any point. To define an angle, we need two rays with a common start point, so we need 3 points overall. In this case, I will label them A, B, and C. We now need to pick one of these points to be the start point for our two rays. Again, for sheer convenience, I'll choose point A. We can now readily construct the line connecting point A and point B, and similarly, the line connecting point A and point C. We may then trivially define the two corresponding rays. The angle is then the figure formed at the intersection of the two rays, as shown here shaded in blue. I am obviously flogging a dead horse here, but it is worth reiterating that nowhere in this construction of an angle have we relied on the fact that point A, point B, or point C correspond to any physical entity whatsoever. Nor does our construction require that either ray correspond to or intersect a physical surface at all. In fairness, in many engineering and architectural applications, both rays do correspond to physical structures. For example, when we require that a wall is approximately perpendicular to the surface on which it stands, or that the walls of a structure meet at some predefined angle. But these are special cases. It is not universally the case that the rays defining an angle need to correspond with anything that is physical. For instance, let's consider a surveying problem where we are trying to determine the vertical angle subtended by some object. First, we take a sighting to some point at the top of the object. Then we take a sighting to some point at the bottom of the object. And finally, the vertical angle subtended by the object is just the angular difference between those two sightings. The construction and measurement of this angle depends in no way on either of the rays A, B or AC corresponding to some physical surface. The same general technique can be broadened to apply to any angle subtended by any 2 points. We first take a sighting on one point, then the other point, and record the angle between the two sightings. Obviously, it's a bit more complicated than that if you want to do it properly, but these are the central elements. Yet again, it's worth pointing out that neither ray AB or AC need to correspond to any physical surface for this construction to work. Similarly, when we're using angles in navigation exercises, we don't need either of our rays to correspond to a terrestrial surface. We construct one ray to point magnetic or true north, a second ray along the line of travel, and then make sure that the angle between these two rays corresponds to the bearing needed to get to our destination. Yet again, it's a bit more complicated in practice than I presented here, but the fundamental truth remains: neither of these rays corresponds to any physical entity. Okay, so there is no requirement in general that the rays defining an angle need to have any sort of material existence. They can be purely mathematical or abstract constructs. Perhaps there's something inherent in the definition of elevation angles that requires one or more of the rays there to have some form of material existence. So what is an elevation angle? An elevation angle is the vertical angular separation between the local horizontal plane and the ray to the object of interest. To determine the local horizontal plane, we must first identify the local vertical. This is most commonly done using a plumb bob. The local horizontal is then the plane lying orthogonal to the local vertical and passing through our point of interest. No part of this derivation relies in any way on the shape of the underlying topography or the regional topography or the shape of the planet. For reasons of pure pedantry, I feel obliged to point out here that it's often stated that the horizontal plane is tangential to Earth at the point where that horizontal is being established. This is only true if we're considering the Earth to be an ellipsoid. On a granular scale, the local horizontal may well intersect Earth's interior, or may not even touch Earth at all. Regardless, to illustrate exactly how irrelevant the shape of the underlying terrain is to the determination of elevation angles, we need only consider observatories. To minimize the effects of atmospheric distortion, most observatories are placed in elevated positions, such as hills, mountains, or promontories. Despite this, observatories are capable of making very precise determinations of elevation angle. We have thus contradicted the claim that the local horizontal bears any resemblance to large-scale topography, regardless of how stridently Mr. Oakley and his adherents wish to assert otherwise. In order to accurately identify the local horizontal plane and precisely level instruments with respect to it, prospective observatory sites are carefully surveyed. In order to detect and correct for the effects of subsidence, compaction, and tectonic movement, the sites are regularly resurveyed, so that at every point in time, the local horizontal plane is well defined. But what if you don't happen to be at a professional observatory, but still want to make elevation angle measurements? How would you go about it? As we discussed just a little while ago, in order to properly define an angle, we need 3 non-identical points. For our first point, we can simply take the detection surface of our instrument. For our second point, we can simply take the celestial object or other marker that we're aiming at. That gives us 2 points and 1 ray. So all we need now is a third point that is somehow related to the horizontal plane. As it turns out, there are multiple techniques for deriving the elevation angle, even when the local horizontal plane is undetermined. The first technique relies on the observer being at some known height above a body of water that extends to the horizon beneath the observed object. In that case, we can use as our third point the point on the horizon directly beneath the target object. This allows us to obtain the second ray and allows us to uniquely define the angle BAC subtended by the two rays. However, this is not the elevation angle to the target object because the ray AC does not correspond to the horizontal plane. Because the point C lies below the horizontal plane, we must apply what is called a dip correction. This correction is a function of the observer's height above sea level and atmospheric refractive conditions. This may be obtained by consulting the appropriate table in a mariner's almanac, and then subtracted from the observed angle BAC in order to give the elevation angle to the target object. I will note in passing that the very existence of dip corrections instantly disproves a common flat Earth claim that the horizon always rises to eye level. Were this in fact the case, there would be no need for dip corrections at all. Our second technique for determining elevation angles may be used anywhere. It doesn't need to be used only at sea, but it does rely on a specialist piece of equipment, a bubble sextant. A bubble sextant contains a spirit level so that the user can tell whether or not the sextant is being held level. That is, whether or not the sextant is being properly aligned with the local vertical vector. In that case, we can use the local zenith as our third point and derive a second ray, allowing us to define our angle BAC. Because of the relationship between the local vertical and the local horizontal plane, we know that our angle BAC and the elevation angle are complementary. That is, they add up to 90 degrees or pi on 2 radians, so that we can easily obtain our elevation angle by simple subtraction. Our third technique relies on placing a container of some reflective fluid in front of the observer. The reflection of the target object in the fluid then forms our third point, allowing us to obtain our second ray and the angle subtended by these two rays, BAC. To get a clearer picture of the relationship between BAC and our elevation angle, we're going to have to zoom in. Okay, that should be enough. Provided our target object is a reasonable distance away, we know that the light coming from that object to the receiver at A is effectively parallel to light traveling to the reflector. We also know that the surface of our reflector is the surface of a fluid, and therefore lies orthogonal to the local vertical, so that the angle between the surface of the reflector and the local vertical is 90 degrees. Which is another way of saying that the surface of the reflecting fluid is effectively parallel to the local horizontal plane. As a result, we know that the angle between the surface of the reflector and the light coming from our target object is just the elevation angle of the object. This is the angle we wish to obtain. By definition, the angle between the incoming ray from the target object and the local vertical is the angle of incidence of this ray. But because of the definition of the elevation angle, we also know that the angle of incidence is just 90 minus the elevation angle. The angle between the local vertical and the reflected ray to the observer is, again by definition, simply the angle of reflection. From the law of reflection, we know that the angle of incidence and the angle of reflection are equal. That is to say, both angles are equal to 90 minus the elevation angle. From these results, we can now obtain the combined angle BCA, which is just the sum of the angles of incidence and reflection, which is a total of 180 minus twice the elevation angle. Now, because the rays AB and BC are effectively parallel, we know that the angles BAC and BCA add up to 180 degrees. That is, they're supplementary. So by rearrangement, we know that the angle BAC is just 180 degrees minus the angle BCA. So BAC is just 180 degrees minus 180 degrees minus twice the elevation angle, which is just twice the elevation angle. So the angle that we measured, BAC, is just twice the elevation angle. Or, rearranging, the elevation angle is just half BAC. This technique was extremely useful in maritime settings, where it was often the case that the horizon is not readily discernible and the ship's motion prevented an accurate vertical angle from being determined. Because water has a tendency to splash around and ripple too much, the reflective surface was often obtained using molasses. Okay, to briefly summarize the results of this video, there is no physical, logical, or geometric requirement that either of the rays defining an angle coincide with any physical surface. In particular, no element of defining or accurately measuring elevation angles in astronomy, geodetic surveying, or celestial navigation requires that the Earth be planar or approximately planar. Oakley's shrill insistence to the contrary is directly contradicted by the fundamental elements of geometry. Okay, that might be a good point to call a halt. I do realize that this is much more fundamental than my normal content and therefore probably even more boring to most people. But I have to admit I couldn't think of any other way to approach the topic other than through geometric fundamentals. Anyway, thank you so much for watching, and I hope you'll join me next time when I'll be attacking the second limb of this argument, distances and elevations on curved surfaces.